In this video, we will investigate several more examples of limits and see some of the standard techniques. So here we'd like to evaluate the limit as x approaches 0 of the given function. Now once again, our intuition is to think x approaches 0. So can I simply take 0 and plug it in for x? And in this case, it doesn't make sense to do so because it would cause us to divide by 0. So that means we need to use some type of algebraic manipulation or standard techniques that we've encountered. And here, the only really algebraic manipulation I see is two fractions, which should be combined into one. But first, let me observe that the denominator of that second fraction can be written a touch differently. We could write this as 1 over x times x plus 1. And that's really indicating to us what our common denominator would be. We can now take our first fraction, multiply by x plus 1, divide it by x plus 1, and still just doing the algebraic simplification. And what we really want to do is get to that point where we can use our limit laws. We now have the limit as x approaches 0. We're going to have a single fraction with denominator x times x plus 1. In the numerator, we'll have an x plus 1 from the first fraction and a minus 1 from the second. And now we just go ahead and cancel. We say, okay, plus 1, minus 1. And we have an x in the top all by itself and an x factored out in the bottom. So with a little bit of algebraic simplification, this becomes the limit as x approaches 0 of 1 over x plus 1. And we're now in the key spot. Looking at what we have, you could either think about breaking it up with limit laws, or you can note that we're taking the limit of a rational function, which allows us by the substitution property, or continuity property, to simply plug in x equals 0. So since this is a rational function, 1 over 0 plus 1, which equals 1. So once again, what this tells us is for an input close to 0 but not equal to 0, the outputs of this function are going to be somewhere close to 1. Another very common example, limit as x approaches 1 of the given function. Now the observation, once again to make, is I cannot simply plug in x equals 1. That would give me 0 in the denominator, and we can't divide by 0. But instead, note there's no maybe obvious algebraic manipulations, but seeing this square root x minus 1 in the bottom, a natural thing we could do is multiply by the conjugate over the conjugate. So that's exactly what we're going to do in this case. So the conjugate is when instead of having, in this case, a minus sign separating those two terms, we're going to turn it into a plus sign. So we are going to multiply by 1 in this fancy way. And remember, when you multiply by 1, you do not change the value of something. But let me make a small kind of side observation. The reason we like this technique of conjugate over a conjugate is if I have a minus b times a plus b. So think a minus b, a plus b. That gives us a difference of squares. That is, it will become a squared minus b squared. So that works out really well when you have square roots, because the square of a square root is going to kind of cancel off. So in the numerator, what we'll have is x minus 1, which is there, times the square root x plus 1. Then in the bottom, we have the conjugate times the conjugate. So we get the first term, square root x, squared, minus the second term squared, which would be 1 squared. And once again, it almost works out too good to be true here. The x minus 1's cancel, and what we are left with is just the limit as x approaches 1 of the square root of x plus 1. So we'll go ahead and break that up into two limits with our limit laws. We can think of the limit of the first plus the limit of the second. The limit of a square root, that's a continuous function as long as we're in its domain where it's defined, so we can just plug the 1 in, and the limit of a constant is always that constant. So the reminder here is that when you see a limit similar to the initial one, which we cannot evaluate directly for whatever reason, and you see that kind of square roots appearing, think maybe conjugate over conjugate if it's made up of multiple terms. So one more example for this video, something on a slightly different vein. Let's evaluate the limit as x approaches 2 from the right of the given function. And here we have to make a maybe very important observation to get started. When we talk about evaluating the limit as x approaches 2 from the right, note that this is a rational function which is undefined at 2, and x minus 2 is not a factor of the numerator. So we can not cancel off this x minus 2. What that indicates for us is that if you were to graph this rational function, it would have a vertical asymptote at x equals 2. So the limit is from the left or the right is either going to be plus or minus infinity. So this limit is going to be plus or minus infinity. And the big question here is which one? So what we have to think about is, since it's the limit as x approaches 2 from the right, if we're just a little bit to the right of 2, what are our function values going to end up being close to? Are they going to be positive numbers going to infinity, or negative numbers causing us to go to minus infinity? So from a graphical perspective, we have a vertical asymptote at x equals 2. We have a root at x equals 3. And if you think about plugging in a number just a little bit bigger than 2, think something like 2.5. 3 minus 2.5 is positive. 2.5 minus 2 is positive. So what the graph will look like then, so it approaches infinity from the right, and because of the form of the fraction here, degree 1 over degree 1, leading coefficient minus 1 and 1, we will have a horizontal asymptote y equals minus 1. So from the left, it's going to look something like this. So as we mentioned previously, the limit as we approach 2 from the right is going to be either plus infinity or minus infinity. From inspection of our graph, we now know that the limit is going to be positive infinity. So just to recap, the limit as x approaches 2 from the right of 3 minus x over x minus 2 is positive infinity.